Hello students, I am Manoj Kundare, the Assistant Professor of Electronic Science. Welcome back to our e-learning platform. In previous video, we have seen the parameters and characteristics of the ideal op-amp and IC 741. The link of the previous video is available in the description box. Please check it. Now, in this video, we are going to see the basic concept about the operational amplifier. Let's see the operational amplifier input modes. There are two input modes, single-ended mode and the double-ended mode. First one, let's see the single-ended mode. If the input signal is applied to only one of the inputs and the other input terminal is connected to ground, it's said to be operating in single-ended mode. That means in this diagram we can see that the input signal here the input signal is connected to the inverting terminal while the non-inverting terminal is ground. Similarly, here the input signal is connected to the non-inverting terminal while the inverting terminal is the ground. That means if the input signal is connected to only one of the input and at the same time the other input is ground, then this connection is called as the single-ended mode. Okay, similarly we can see the differential mode or double-ended mode. In differential mode, two opposite polarity signals are applied to the two inputs of the op-amp. The difference between the input signal is amplified appears at the output. That means in this diagram we can see that there is at both the inputs, that means for the non-inverting terminal the one supply is given and for inverting terminal the inverting terminal the one supply is given. Also for non-inverting terminal the other input supply is given. This type of connection is known as the differential mode or double-ended mode. Okay, then the third one is the common mode. In this common mode operation, the same input signal is applied to both the input terminals. Ideally, a zero voltage should be produced by the op-amp. Here, this is the configuration of the common mode signal. If we see the diagram, then we can see that both the non-inverting and the non-inverting terminal are common together and the input signal is given to it. That means here V1 is equal to V2, but op-amp is the differential amplifier, hence it can amplify V1 minus V2, but V1 equal to V2, hence V1 minus V2 has the value 0. Its differential value is 0, then ideally the op-amp cannot amplify anything, hence the value of Vout is also 0 volt. I hope you all understand this common mode connection. Now let's see the configuration of the operational amplifier. There are two types of configuration, open loop configuration and closed loop configuration. Let's see first open loop configuration. In open loop configuration, there is no feedback from output to input. That means in this type of configuration, there is no feedback. That means no part is connected to the input like this or like this. Okay. The differential signal present between the inputs will be amplified by its open loop gain. AV is equal to 2 into 10 raised to 5. That means in open loop configuration there is no no feedback is connected like this. Okay, feedback means the part of output is connected back to the input like this. Okay, that means at this stage in open loop configuration the operational amplifier will amplify the differential inputs with the gain 2 into 10 raised to 5. This is the open loop configuration. Therefore, for very small magnitude of the differential voltage output will reach the positive or negative saturation. Let's see why the op-amp is not used as an amplifier in open loop configuration. The op-amp is not used in the open loop configuration. Let's see, due to very open loop gain, distortion is introduced in the amplified output signal. That is, due to open loop configuration, distortion is introduced in great extent in the amplified output. The open loop gain does not remain constant, but varies with temperature and power supply as well due to mass production technique. That is, the gain is not stable due to temperature and power supply fluctuations. The bandwidth of the op-amp is very small, almost equal to zero. For this reason, the open loop operational amplifier is not used in practice as an amplifier. Okay, I hope you all understand why the open loop configuration is not used in amplification purpose, because distortion is added into the output voltage. The gain is not constant because of temperature and power supply fluctuation, and bandwidth is very small, that is almost equal to zero. These are the reasons that's why the op amp is not used as an amplifier in open loop configuration. Hence, for the amplifier, the closed loop configuration is used. Let's see the closed loop configuration. In closed loop configuration, a feedback is introduced, that is, the part of output is fed back to the input. The feedback can be of following two types: positive or regenerative feedback and negative or degenerative feedback. These are the examples of positive and negative feedback. In this positive feedback, we can see that the feedback is taken from output terminal through the resistor to the positive terminal, hence it is named as the positive feedback. Similarly, if the output terminal is connected to the negative terminal through the resistor, then this type of feedback is known as negative terminal. The main difference is that for positive feedback, the positive terminal is used, and for negative feedback, the negative terminal is used. I hope you all understand the positive feedback and negative feedback. Let's see once again the positive feedback. If the feedback signal and the input signal are in phase with each other, then it is called as the positive feedback. It is used in applications such as oscillators and Schmitt triggers or regenerative comparators. That means in positive feedback we seen the connections here. In positive feedback, the input is given to the non-inverting terminal, that means to plus like this V in, while the inverting terminal is ground. The output is taken from V out terminal and connected to the non-inverting terminal through the resistors. Here, if the V in has this phase, then V out also has this phase. That means there is the 0 degree phase shift. That means there is no change in the phase of the input signal of the amplifier. I hope you all understand the positive feedback. Now let's see the negative feedback. If the signal feedback to the input and the original input signals are 180 degree out of phase, then it is called as the negative feedback. In application of op amp as an amplifier, the negative feedback is used. That means when the input is given to the inverting terminal and the feedback is taken from the output terminal and the negative terminal through the resistor, then this configuration is called as the negative terminal. If the input signal is in this phase, then the output signal get in this phase. That means there is 180 degree phase shift in the negative feedback. I hope you all understand the difference between the positive feedback and negative feedback. Let's see the advantages of negative feedback. The negative feedback stabilizes gain. It reduces the distortion. It increases the bandwidth. It reduces the effect of variations in temperature and supply voltage on the output of the op amp. The only disadvantage of the negative feedback is its low gain. That is, the only disadvantage of this negative feedback that it has the low gain. Okay. Now let's see the main topic, the concept of virtual short. What is virtual short condition? According to the virtual short concept, the potential difference between the two input terminals of op amp almost zero. That means, according to this concept, the potential difference, that means the voltage between the two input terminals of the op amp, is almost zero. In other words, both the terminals are approximately at same potential. Let's see here, the input impedance of the op amp is ideally infinite. That means the value of this resistance or the input impedance is ideally infinite. Hence, current flowing from one input terminal to the other will be zero. This resistance has the value infinity. Hence, whatever current flowing through this terminal is not enters into this terminal. Okay. Thus, the voltage drop across Ri will be zero and both the terminal will be at the same potential, means they are virtually shorted each other. That means we can see here that in this diagram there is a input resistance between or the input impedance between the V1 and V2 terminal, that means inverting and non-inverting terminal, and its value is infinity. There is the potential, there is no current flow between the input impedance, hence no potential develop across this resistance. The potential developed across input impedance is almost equal to zero. Hence, the V1 and V2 are at the same potential. Hence, this is known as the virtual short condition. Now, let's see the concept of virtual ground in operational amplifier. What is the virtual ground in operational amplifier? As the name indicates, it is the virtual, not real ground. That means this is the virtual ground. This terminal is not actually connected to ground. Okay. In op amps, the term virtual ground means that the voltage at that particular node is almost equal to the ground level or the zero level. That means if this has the zero voltage, then at this point the voltage is also zero, but it is not connected actually to the ground. This point is not connected actually to the ground, but its potential is zero. Hence, this point is known as the virtual ground point. Okay, it is not physically connected to the ground. Let's see how the virtual ground concept is employed in inverting amplifier. We already know that the ideal op amp will provide infinite voltage gain. That means the gain is infinite, but the formula of the gain is equal to V0 upon V in. That means output voltage upon input voltage. If we rearrange this, then we get V in is equal to V0 upon or V out upon gain. As the gain has the infinite value, that means V0 upon infinity, then we get V in is equal to 0. That means the value of input is equal to 0. But V in is V2 minus V1. V in is V2 minus V1. Hence, V2 minus V1 is equal to 0. By this, we get V1 is equal to V2. Okay. In this circuit, V1 is connected to ground. So, that means this V1 is connected to the ground. Hence, it has the value 0. But V1 equal to V2. Hence, V2 will also add the ground potential, that is V2 is equal to 0. I hope you all understand this explanation. Let's see once again. Here in this diagram, we know that there are two signals. This is V1 and this is V2. We know that the gain of the amplifier, that is the gain V0 upon V in, is infinity. Okay, by arranging this term we get V in is equal to V0 upon A. Let's see once again. Here let this is V1 terminal and this is V2 terminal. Okay, the gain of the amplifier A is equal to V0 upon V in, but the gain is having value infinity, hence we get V0 upon V in. If we rearrange this term, then we get V in is equal to V0 upon gain A, but the gain has the value infinity, that means V0 upon infinity, we get the value of V in equal to 0. Okay, the value of V in is 0, but V in is equal to V1 minus V2. Therefore, V1 minus V2 is equal to 0 because V in has the value 0. Due to this, we get V1 equal to V2. Okay, V1 equal to V2. Then here the V1 has value 0, hence V2 also has the value 0, that means this point also has the value 0, that means it is virtually connected to the ground, hence it is known as the virtual ground concept. I hope you all understand the virtual ground concept. Thank you.